Okay, so this is probably going to be the most challenging section really for the year. I do want to cover it. I think it's important that you know it. It is not part of a traditional first year STEM calculus course, but I think you guys know, well, I know you guys can handle it. If this were standard in-person kind of stuff, not only would I cover it, but I'd put a question on the test from this section. I'm just going to tell you right now, I'm going to put a question on the test, but it's going to be a bonus. So this is strictly going to be bonus, kind of FYI. I still want you to do the homework and everything, but I'm not going to put this as part of the regular test because I think it's really challenging to do in this format. So I'm going to go pretty quickly through this. It's a little bit of a longer section, but obviously you have the ability to replay the videos, so we'll be fine. So remember this as close as stuff was in our other definition, and that's not really a definition. So this is a precise definition. This is more of the kind of the big boy or big girl definition of a limit, if you will. It gets rid of that phrase "as close as," because one person's "as close as" is not as close as another. So this will eliminate it. Plus, it introduces you to some techniques and higher level stuff. So that's what we're going to cover. So here's a traditional standard run-of-the-mill piecewise function, right? If x is 3, the output is 6. Otherwise, it's that line. Notice that the limit as x approaches 3 of this function should be fairly straightforward, right? That means this piece applies, and so it's going to be 5. Okay, so there's no mystery in that one. It's a straight up direct substitution from the previous section, but going back a little bit further, what does this mean in terms of the definition? Well, remember, it means we can make the function n5 as close as we want by picking values of x sufficiently close to but not equal to 3. So again, to get rid of that language, let's go to some specifics. So how close to 3 do I have to get so that the function differs from 5, like less than 0.1, okay? So we're going to need to establish some definitions here. Absolute value measures distance. So absolute value of x minus 3 is the distance from x to 3. This is, of course, on the x-axis. And f of x minus 5, the absolute value of that, is the distance from f of x to 5. Clearly, that's on the y-axis. And so the idea here is, well, if I'm going to differ by less than 0.1, that means I can go as high as what? 5.1. So I have 5 plus or minus 0.1. So I can go as high as 5.1 and as low as 4.9. And basically, how do I land in that window? So here's kind of, let's skip this for a second. We'll come back to that in a second. Let's look at a graph. So the question for this one is, here's the graph of f of x. We said 0.1, right? So we're going to call this 5.1 and this 4.9. Okay. Now, we should be able to find these pieces here. So if you go over to the graph, right, and then go down, this I should be able to find this number here. 5.1, if I go over to the graph and then go down, right, sorry, not quite far enough there. If I go over to the graph and then go down, I should be able to find this number, right? And you can just kind of work backwards, right? So if you know when x is not 3, right, f of x was, what was it, 2x something, plus 1, minus 1, I forgot already. It was 2x minus 1, sorry. So it was f of x was 2x minus 1. So if we want to get 5.1, right, that's 2x minus 1, and we can just solve for x and find that value here. And then if we solve for 4.9, right, 2x minus 1, we can go ahead and find that value here as well. So let's go back now to where I was. So this number here, we're going to assign these things number. So this piece right here, this plus or minus on the y-axis, that's going to be called epsilon. Okay, it's a Greek letter epsilon. This corresponding value here on the x-axis is going to be called the Greek letter lowercase delta. Okay? So what this is saying is we need to find a number, which we're going to call delta because we're trying to find it on the x-axis, such that if we're within that, that forces our function to be within 0.1 of 5. In other words, if we can find a number on the x-axis so that it forces our y-axis window to go from 4.9 to 5.1. And just let's notice, if you did the actual math like I set up before, I didn't actually do it, but if you did it, you would find that 0.05 would actually work, okay? So if you take this 0.1 and divide it by 2 and get 0.05, I'm claiming then that if x is between 2.95 and 3.05, that will imply f of x is between 4.9 and 5.1. Okay, that's my claim. And you can actually plug those values into the function and test it, and it does come out true. Okay, it comes out. So we have found a delta. The delta is 0.05, and that works to answer this initial question. So right here, how close to 3 do we have to be so f of x differs by less than 0.1? Well, we have to be within 0.05. Okay, we actually found an answer to that. So what happens if I change the 0.1 to 0.01? Do you think the same delta will work? In other words, now the y window is what? Well, 0.1 was 4.9 to 5.1, so 0.01 is 4.99 to 5.01. So I've tightened the window up significantly. Do you think that whatever we came up with, 0.05, do you think that that same delta worked? No, obviously not. And you can run the numbers, okay? You would need to find a new delta. And again, we can work backwards and you would find it to be 0.005. I'll let you guys do that on your own. Now, how long can we play this game? Well, obviously, yeah, forever, right? This can go on for quite a while. That's not the point. What's the point? The point is, well, how do we find one in general, right? How do we find one so that no matter what epsilon someone gives you, the delta will always work? Well, in order for that to work, obviously it can't be a number. It has to be related to the epsilon. So notice that this first example, how did we find delta? Well, we took epsilon and we divided it by 2. Okay. Guess what works in the second one? Well, the same deal, right? This would be the new epsilon divided by 2. Okay. So this is, excuse me, what I have here, right? So it doesn't matter what is given to you for the y-axis window. As long as you take that number and divide it by 2, you should be okay. Anybody want to take a guess as to why this? Again, this is only for this particular problem, but anyone want to take a guess as to why this will always work? Why the 2? Why dividing by 2? Well, because this is a straight up linear function, and notice that the 2 is the slope, right? So it's the rate of change. Okay, it's the relationship between this window and this window. It's based on the rate of change. Okay, so linear functions, this is a very easy process. It gets pretty interesting when we get outside of linear. And so this kind of brings us to the actual formal definition. So don't get too freaked out by all the all the symbols here. It's really not that bad. So this you should recognize, right? That's exactly the same thing that we had before. The limit as x approaches a, have f of x is equal to L. Now what that actually means is as follows. So this upside down A is read for all. So for all epsilon greater than 0, okay, this backwards E is there exists there has to exist a delta greater than 0 such that if you're in the if you're in that plus minus delta window of A, that will imply you're in that plus minus window epsilon of on the y-axis. Okay, so again, think about it this way. There's one way to say that these two things are equal, f of x and L. Okay. If I say that they're closer together than any positive number, what does that mean? Well, it means they're equal. Okay, so if the distance between them is less than any positive number, it means they're equal. So that's essentially what this is saying. For any given epsilon greater than 0, so no matter what number somebody gives you. So in that or in the previous example, if someone gave you this tiny, 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 tiny number, if that limit exists, then there has to be some delta that you could find that would make it work. Okay? So for any epsilon greater than 0, there has to exist a delta such that to get in that y window, the given x window will work. That's essentially what it's saying. So there's no as close as in this. So this is a more precise definition. So I'm already up to about 11 minutes here for this video. I think I'm actually going to break this guy into 2 parts because it's a lot. So we're going to end here with the definition, and then I'm going to pick up part 2 of this video right with this definition. I'll go kind of back over it very quickly, then we'll do a specific example, and then we'll get into how you actually prove these things.